My name is Rebecca. I'm a first year student here at St Anne's studying material science, and in this video I'm going to talk to you all about deformation. Your first question might be, what is material science? It's hard to do it justice in one sentence, but we study the properties of materials, the science behind those properties, and how we can use that knowledge to change the material's properties. These pictures and drawings all link to what I'm going to talk to you about today, so hopefully by the end of the video you'll have worked out why. One of the properties I've been studying this term are the mechanical properties of a material. These are the properties of a material which are linked to deformation. There are two types of deformation, elastic deformation and plastic deformation. In elastic deformation, once the force is taken off the material, it will return to its original shape. A good example of this is an elastic band. Normally you can stretch it and it will go back to how it was. Sometimes you stretch it a little bit too much and it won't return to its original shape, and this is called plastic deformation. If you pull hard enough, fracture will occur and your elastic band will be broken. This is definitely something we want to avoid as material scientists. We need to be able to measure the behaviour of the material under load or force to determine the strength of the material. At school you might have plotted a force extension graph and shown that Hooke's law was true, as long as you didn't stretch your spring too far. Hooke's law is that the force applied to the material is directly proportional to the extension, or F equals kx. This means if I add 1 Newton of force and my spring extends by 1 centimetre, that if I add 2 Newtons of force, it'll extend by 2 centimetres. But the size of the spring you're using will affect these values, and that's why we convert our force and extension into stress and strain. Stress and strain effectively normalises these values so we can compare results for objects of different sizes. Stress is equal to the force divided by the cross-sectional area, and the strain is equal to the extension, or the change in length, divided by the original length before we added any force. I've drawn a typical stress-strain curve for the metal on the slide. I've labelled some key points on this graph, and we might compare these values between different materials to work out what their properties are and what they're good at. A key constant we use to compare materials is the Young's modulus. This is a measure of stiffness of a material, or how well a material withstands deformation when we apply a force. You can find it by calculating the gradient in the elastic region of the stress-strain curve. The yield stress is also important. This is the start of the plastic region, where we start to permanently change our material. Different materials have different stress-strain curves depending on their structure and how they were manufactured. For the rest of this video, we're going to focus on metals. In school, you might have learnt about the metallic bond and metallic structure as a regular lattice of positive ions surrounded by a sea of delocalised or moving electrons. However, we don't live in a perfect world, and defects exist within this structure. Dislocations are a type of line defect which are behind a lot of the key properties of metals. It's like adding an extra column of atoms to the top of your metallic structure, but not the bottom. Dislocations allow us to break less bonds in a metal when we apply a force, as less bonds have to break. Only the dislocation moves, not all the atoms on the top half. They allow metals to change shape and give us loads of cool properties. They allow you to bend a paperclip, and when you do, the dislocations move at a speed of hundreds of meters per second. They allow metals to behave like super strong plastics rather than brittle ceramics. But how do we make metals stronger? We can make alloys. We add other elements into the metal which make it stronger. These elements can be interstitial or substitutional. Interstitial atoms are much smaller than the host metal and they sit in the gaps between the host metal atoms, whereas substitutional are a similar size and they sit on the same sites as the host metal. Both of these can make the metal stronger because they stop dislocation motion from happening as easily. They add extra energy that the dislocation has to overcome to move, so we have to increase the force in order to deform the metal. We can also increase the strength through heat treatments to produce precipitates of these interstitial or substitutional atoms. This creates sections of another material within the structure and also increases the energy for dislocation motion. Heat treatments can change the microstructure of the alloy, which can also affect the strength, as different microstructures form under different heat treatments and have very different properties. This is why there are loads of different types of steels, aluminium, alloys out there, which all have different properties and are used in different ways. If you want to find out more about material science, I would recommend giving Stuff Matters a read. This book is aimed at anyone who's interested in science, and you can find out about a variety of different materials, including chocolate. If you're an A-level student and you'd like to research further into what I've been talking about today, I'd really recommend reading The New Science of Strong Materials. Thank you for watching.